So this slide right here is a summary of foliated textures. As you can see, they're classified based on metamorphic grade, as we have talked in the past few slides, with slaty texture being the lowest grade foliated metamorphic texture, and the gneissic texture being the highest grade foliated metamorphic texture. Mecmatite or mecmatitic texture goes even beyond gneissic texture, as we'll see at the end of this chapter a little bit. So in this case, mecmatite is exposed to extreme environments, which causes that highest of all possible metamorphic grades. And in fact, it goes into such extreme environments that it even enters the realm of igneous rocks a little bit, because there's a little bit of partial melting. So as you get into higher grade metamorphic foliated textures, you're going to have larger minerals that are visible. And usually these are resulting from the recrystallization. So typically any metamorphic rock containing a large amount of accessory minerals, or uncommon on a vast majority of rocks, are named with that accessory mineral at the beginning of the rock name. And then that is followed by the texture type. So that was a little bit confusing, but for example, if a schist contains a lot of garnets, which is a pretty common thing to happen, this is going to be called a garnet schist. So the accessory mineral in this case is the garnet, but there's a high amount of them compared to most other types of rocks or even types of schists, and so it's called the garnet schist. So I would also like to point out from the slide the specific rock for each of the different textures. Hopefully you will be able to do it, but again, this is going to be the slate, this is going to be the phyllite, this is going to be the schist, this is going to be the gneiss, and this is the mecmatite. So you see that in slate, no visible grains, it's kind of dull looking. The phyllite, it starts getting a little bit of a glossy sheen to it. In the schist, there's a glossy sheen, and if we were to look at a sample with, I guess a better sample, we'd be able to see specific mineral crystals. The gneiss is going to have that banded appearance of light and dark colored minerals, and then the mecmatite looks kind of like gneiss, but it's almost as if though those bands have been heated to an extreme degree and have been able to mold plastically, ductily. In contrast to foliated textures, non-foliated textures are those where there is no alignment and parallel lines of the minerals within the rock. They typically form in environments where the deformation is minimal, or when the parent rock itself is composed of minerals that develop equidimensional crystals rather than the tabular or elongated shaped crystals. So these textures tend to develop where there is no differential stress overall, as we'll see later on as well. Many times they form by contact metamorphism, so they are basically baked by the nearby flowing magma body. We'll look at this different environment of metamorphism, or metamorphism environments, I should say, a little bit later in the chapter, so you get an idea of what I mean by areas that have no differential stress, or areas that have that contact metamorphism. But again, basically it's the baking of the rocks that are surrounding a magma body that is at depth. So the non-foliated textured rocks are, or I should say a few of the common rocks from non-foliated textures are marble, for example, which is a metamorphosed type of limestone, or equivalent to limestone. Its chief mineral component is calcite. Marble is easy to cut and shape because calcite is very soft. So many of the monuments that humans have made are made up from marble itself. For example, the Taj Mahal in India is made out of marble, or the Lincoln Memorial in Washington, D.C. is also made out of marble. Most marbles are kind of gray to white, but some of them are pinkish or even green. or even have little black lines to them, and this is due to the different impurities that the parent rock had. Another common non-foliated textured metamorphic rock is quartzite, which is a metamorphosed type of sandstone. So quartzite is very hard, as the quartz grains that have fused together basically make up the rock. Pure quartzite is white, but many times it contains impurities that make it be a little pinkish or greenish. This type of impurities are many times related to the iron oxides that cemented the rock together as a sedimentary rock, and then once it became metamorphosed, the color remained. Or it can be iron oxides that were flowing as ions dissolved from nearby waters too. Another non-foliated textured metamorphic rock is hornfels. So hornfels is a metamorphosed rock from clay-rich rocks. It typically gets baked by the magma bodies that are nearby at depth, so it usually forms as contact metamorphism. And it is usually gray to black in color, as you're seeing right here. And finally, we have anthracite. Anthracite is this guy right here, and it is a metamorphosed coal, basically. I also forgot to point out this top one right here is a marble, and then the quartzite is going to be this one. In this case, it's a little bit greenish, as you're seeing. The images that you're seeing over here are of sandstones on the left, so you're seeing the quartz grains kind of flowing within the cement. They have a lot of pore spaces in between them, and it doesn't seem like they have any constraint in terms of the space that they have between each grain. And then the image on the right is the quartzite sample showing all of those quartz grains basically fused together. So all that empty space that used to be between the grains is now gone. Okay, so most metamorphic rocks come from shale, from limestone, and from sandstone, which are the surface parent rocks to these type of rocks. Shale is the most common parent rock to foliated textured rocks like slate, phyllite, schist, and gneiss. Mostly slate, phyllite, and schist. The sequence of metamorphic rocks is going to reflect an increase in grain size with increasing metamorphic grade, and a change in the rock texture, and also a change of mineralogy. And we'll go through these, and we have been going through these, I should say, as well, in the last few slides, and we'll go through them in the next few slides as well. But again, with a change in the metamorphic grade, there will be a grain size change, a change in texture, and a change in mineralogy. The table that you're seeing on the slide is a pretty good summarization of the main metamorphic rocks that you're going to see in lab and in real life, hopefully. So these are the most recognizable based on their texture and some of their mineral composition as well. We saw all of them in the last few slides, which made up the different textures, either foliated or non-foliated, and we will be seeing them in lab again. So I won't go too in-depth on this graph, but I encourage you to take a better look at it on your own before lab, so you're more familiar with what you're looking at. All right, so there are many different metamorphic environments in which metamorphism can occur. Most of them occur near plate margins, and many of them are associated with igneous activity. So we'll go ahead and go through them all, or most of them. The figure in the slide that you're seeing there illustrates the fact that the different types of metamorphism occur over a certain range of temperatures and pressures. So for example, the hydrothermal metamorphism right here occurs over relatively low temperatures. So temperatures is the x-axis right here, pressure the y-axis. So you're seeing hydrothermal metamorphism occurs at low temperatures and also relatively low pressures. But contact metamorphism, for example, occurs at very high temperatures, but also low pressures. For example, burial and subduction metamorphism typically occurs at pretty high pressures and temperatures that are not necessarily very high. And then regional metamorphism occurs over a very wide range of temperatures and pressures, and it gets all the way to the highest temperatures, almost all the way to the highest pressures. Okay, so differential stress is typically needed for regional metamorphism to occur, as well as for burial and subduction zone metamorphism. But it's typically not needed for contact or hydrothermal metamorphism, which partly is going to explain why these two latter ones that I just said, contact and hydrothermal, do not require very high pressures for metamorphism to occur. And again, we'll go through all of these environments in more detail, but I just want to point out these things while you're still looking at this graph. Okay, so the first one we're going to look at, or first two, are contact metamorphism and hydrothermal metamorphism. Contact, or otherwise termed thermal metamorphism, occurs in the Earth's upper crust when the rocks are immediately surrounding a molten igneous body, so usually an intrusive igneous body at that point, and when they get baked by the high temperatures from that nearby igneous body. So in this type of metamorphism, there is typically less pressure than at further depths, where other types of metamorphism occur, as we'll see in the next few slides. So the resulting rocks from contact metamorphism are typically not foliated because they're not subject to differential stress, to that pressure that is needed for differential stress to occur. Contact metamorphism alters rocks which are in the discrete zone adjacent to that heat source, which is called the I don't know how you say it exactly, areole, but it's going to be, let's see if it points out right here. Yep. So metamorphic areole. So you're seeing that it is that band that is immediately surrounding the magma body itself. So in this case, it's shown as purple. This is going to be the whole areole. Okay. So the emplacement of small intrusions, for example, like dikes or sills, which are, as we saw in Chapter 4, intrusive tabular bodies of igneous rocks, typically form areoles that are only about a few centimeters in thickness because they're typically small intrusions. But larger igneous bodies like batholiths or stalks can produce areoles as large as kilometers. So they tend to alter these rocks for kilometers away from the heat source itself. So the areoles can be very, very large. The areoles themselves typically consist of distinct zones of metamorphism, with higher degrees of metamorphism occurring nearer to the magma body, as is to be expected, where the greater temperatures are, and lower degrees of metamorphism occurring further from the magma body, where the lower temperatures will be by the conduction of the heat itself. Typical rocks that form from the contact metamorphism are things like hornfells, which is again metamorphism of mudstones with clay-rich minerals. But you can also have quartzite, which is again the metamorphosed form of sandstones, and you can have marble, which is the metamorphosed form of limestones from these type of metamorphism. Okay, hydrothermal metamorphism occurs when hot, ion-rich water circulates through pore spaces or through fractures within a rock, which causes chemical alteration. So remember from a few slides back that hydrothermal solutions contribute to metamorphism by enhancing the recrystallization of existing minerals. These fluids will also facilitate the movement of the ions into and also out of different rock bodies, which will overall change the chemical composition of that rock body.